Welcome to the deep dive. We're here to tackle some of the biggest, most beautiful, and most frustrating riddles in the universe and bring the insights straight to you.
And today's topic is maybe the biggest and most frustrating of them all.
It really is. We are wrestling with a particle that is, by all accounts, essential. It has to exist for the cosmos to work in a way that makes any logical sense. But it's also a ghost in the machine of reality whose very existence is, well, it's shielded from us by the very laws of physics that demand it.
It is, without a doubt, the deepest theoretical puzzle in modern physics. We're talking about the graviton, this hypothetical massless spin-tube boson that we absolutely need to finally unify quantum mechanics with the grand architecture of space-time.
You know, I want to start by pushing back against a title that's been in the media for years. Everyone calls the Higgs boson the God particle.
Right, that was the big one.
And look, finding the Higgs was a monumental achievement, no question. It's the particle that gives mass or inertia to all the other fundamental particles.
It explains why things have heft, why they resist being moved.
Exactly. It explains why matter is, well, mattery. But if you're really talking about the particle that sets the stage, the one that defines the actual fabric of reality that all that matter dances on, then the real God particle has to be the graviton.
That's a really good way to put it. The Higgs explains the actors, but the graviton explains the stage itself.
Right. The Higgs gives things mass, but the graviton, if we can call it that, dictates the curvature and the very structure of the universe.
It's a necessary recalibration, I think. The graviton is the particle of geometry. It's the final, glaringly empty slot in the standard model of particle physics, and it's the one piece we need to solve the puzzle of quantum gravity.
So that's our mission for this deep dive. We're going to put this theoretical specter under the microscope. First, we'll break down the theoretical mandates, why it absolutely must be massless, and why it must have this strange property, spin 2.
These aren't just guesses. They're logical necessities.
And then we're going to pivot to, well, the profound tragedy of it all. We'll get into the immense physical barriers that make it impossible to detect. We'll tackle the hierarchy problem and the, frankly, brutal mathematical limits laid out by the Rothman-Bohm calculations.
And you'll see this incredible, almost poetic irony. The very theory that predicts the graviton also predicts this inescapable cosmic censorship that hides it from us forever.
All right, let's start at the very beginning of this conflict. And it's not a conflict born from failure, is it? It's a conflict born from two theories being, well, too successful.
That's the perfect way to describe it. We have these two pillars of 20th century physics, and in their own domains, they are spectacularly, unbelievably accurate.
Pillar 1, the standard model.
Right. It describes all of matter, the fermions, and 3 of the 4 fundamental forces. You've got electromagnetism, the weak nuclear force, and the strong nuclear force. And does this using the language of quantum field theory, or QFT.
And QFT's big idea is quantization. Everything comes in discrete little packets. Forces aren't smooth fields. They're mediated by an exchange of particles, these bosons. You have photons for light, gluons for the strong force, W and Z bosons for the weak force. It's all granular, pixelated.
Exactly. The standard model is quantum from the ground up. Then you have the other pillar, Einstein's General Relativity, his theory of gravity.
Which is the polar opposite. GR doesn't describe gravity as a force mediated by particles at all. It's pure geometry. It's the curvature of this four-dimensional fabric we call space-time.
It's classical. It's a smooth, continuous rubber sheet that gets warped and bent by mass and energy. No packets, no pixels, no quanta. Just elegant, seamless geometry.
And that's the core of the problem, right? The source of gravity, the matter and energy that does the bending is fundamentally quantum.
Precisely.
Yeah.
You take an electron, according to quantum mechanics, it can be in a superposition of 2 different places at once.
Yeah.
It lives in this fuzzy cloud of probability. It obeys the uncertainty principle.
So, how can a fuzzy, probabilistic quantum source generate a perfectly smooth, well-defined classical gravitational field? It feels like a contradiction.
It's a deep mathematical and logical inconsistency. If you try to couple a classical gravitational field to a quantum source, you run into paradoxes immediately.
Like what? What's the thought experiment there?
Well, imagine a big, heavy object. Let's say it's in a quantum superposition of being in location A and location B.
Okay.
According to general relativity, it should be generating a smooth, classical gravitational field.
Yeah.
But which one? Does it generate the fields for being at A or at B or some weird average? If you say it's an average, that's not what GR allows for a single object. If you say it's one or the other, what makes the choice?
So the gravitational field itself would almost be measuring the quantum object, forcing it to choose a position.
That's one of the frightening possibilities. If gravity stays classical, its interaction with the quantum system could force that system out of superposition. It could collapse the wave function. That would violate all sorts of fundamental quantum rules.
So the field has to be able to follow the quantum weirdness of the source.
It has to. And for the field to be fuzzy and probabilistic like its source, the field itself must be quantized. It has to have a particle mediator, just like every other force we know. It needs a graviton.
Okay, so there's a mandate for quantization. But GR is famously complex. The equations are non-linear, a real nightmare to work with. How do physicists even start to look for a particle hiding inside that mathematical structure?
They do what physicists always do when faced with a horribly complex problem. They simplify it. They use what's called the linearized approximation of general relativity.
Meaning you assume gravity is really, really weak.
Which, for most situations, it is. The idea is that you treat space-time as being almost perfectly flat with just tiny, tiny ripples on top of it.
This is that famous equation, isn't it? The metric equals the flat metric t plus a small perturbation.
That's the one. You start with a perfectly flat background of empty space, the Minkowski background, Tutamunyo. Then you add this tiny ripple, which is your weak gravitational field. And you assume this ripple is so small, you can ignore any terms where it interacts with itself.
It's like looking at the surface of a huge, calm lake and only paying attention to the tiny waves from a single raindrop, ignoring how those waves might bump into each other.
Perfect analogy. And once you have those simplified equations of motion for that little ripple, you can apply the standard rules of quantum field theory to it, the same rules that give you the photon from the electromagnetic field.
And when you do that,
the math tells you that this propagating ripple, this wave, is actually a particle, a quantum packet of gravitational energy.
So the graviton isn't something they just made up to solve a problem. It's the mathematical consequence of applying quantum rules to the geometry of space-time.
It falls right out of the formalism. That field is what we call a tensor field. It has two indices. And when you quantize a tensor field like that, it mathematically corresponds to a particle with spin 2. And finding it, well, that would be the final proof that space-time itself isn't a smooth sheet. It's granular. It's pixelated at the tiniest possible scales, the Planck scale. The graviton is that pixel.
The ultimate building block of reality, assuming we could ever, actually see one.
Well, that's the catch.
Okay, let's dig into the DNA of this particle. If it exists, theory demands it has two very specific, non-negotiable properties. It must be massless, and it must be spin 2. Let's start with mass. Why 0?
The masslessness is a direct consequence of the range of the gravitational force. We see gravity acting over the entire observable universe. There's no distance where it just seems to cut off.
And this connects back to an idea from particle physics called Yukawa theory, right?
Exactly. Hideki Yukawa showed that the range of a force is inversely proportional to the mass of the particle that carries it.
So a heavier particle means a shorter range.
A much shorter range. The force potential he described has this exponential decay term in it, EDMEC. If the mass ME is large, that term becomes huge very quickly as the distance r increases and the force just vanishes.
That's what we see with the weak nuclear force. It's carried by the W and Z bosons, which are very heavy, and so the force basically only works inside an atomic nucleus.
Precisely. But with gravity, we see its effect holding galaxy clusters together millions of light years across. We observe its classic inverse square law, 1 over r squared, holding true as far as we can see. There's no sign of that exponential decay.
So for that decay term to disappear, the mass in the exponent has to be 0.
It has to be exactly 0. That's the only way to get an infinite range force. And that also means the graviton, just like the photon, must travel at the speed of light, c.
But physicists are clever. They're always trying to find loopholes. I know there have been theories of massive gravity. What happens if you try to give the graviton just a tiny, tiny bit of mass?
You walk straight into a minefield of theoretical problems. The most famous one is called the VDDZ discontinuity.
Van Dam, Veltman, and Zakharov.
Right. And what they found is that there's no smooth transition. You can't just take the theory of a massive graviton and have it gently become general relativity as the mass goes to 0. The moment you introduce any mass, milliram, dollars, no matter how small, the predictions of the theory become violently different from what we observe.
In what way? What's the key observable that breaks?
The bending of light. General relativity makes a very precise prediction for how much the sun's gravity should bend the light from a distant star. It's about 1.75 arc seconds.
A prediction that's been confirmed over and over again for a century.
Exactly. But if you calculate the same thing using a simple massive gravity theory, even as you let the graviton's mass approach zero, you don't get 1.75, you get 3/4 of that value, about 1.31 arc seconds.
Wow. So even an infinitesimally small mass leads to a 25% error in one of the most fundamental tests of gravity.
It's a discontinuity, a hard break in the physics.
Yeah.
And Sir Arthur Eddington's 1919 eclipse expedition already proved the 1.75 arc second value was correct. So the simplest versions of massive gravity were ruled out before they were even fully formulated.
And what about the more complicated versions?
They often introduce even worse problems. To fix the discontinuity, you end up with instabilities in the theory, things called ghost modes. These would be particles with negative kinetic energy, which would mean the vacuum of space itself would be unstable, constantly able to decay and spit out energy from nothing.
A universe that would just tear itself apart. Okay, so masslessness is locked in. It's not just a preference, it's a requirement. Now for the really unique part, spin 2. Why spin 2?
This comes down to the symmetries of the gravitational field itself. And the way we classify particles in QFT is through something called Wigner's classification, which uses the fundamental symmetries of spacetime.
Rotations, boosts, all the ways you can move around without changing the laws of physics.
Right, and for massless particles, it's a bit special. They don't have spin in the same way a massive particle does. They have a property called helicity, which is the projection of their spin onto their direction of motion. And a key result is that any massless particle only has 2 helicity states.
Yeah.
Plus h and minus h.
Only 2, regardless of what its spin number is.
Only 2 physical states. And for the graviton, those 2 helicity states correspond perfectly to the 2 polarization states we've actually detected with gravitational waves.
The plus and cross polarization.
Exactly. The stretching and squeezing of space-time.
Okay, so why does that stretching and squeezing pattern mean it has to be spin 2? A photon is spin 1, and it also has 2 polarizations.
It comes down to rotation. The spin of a particle tells you how much you have to rotate its field pattern before it looks the same again. For a spin 1 photon, its polarization pattern looks like an arrow. You have to rotate it a full 360 degrees to get it back to where it started. But for a gravitational wave, the pattern of stretching in one direction and squeezing in the perpendicular direction, well, it has a higher degree of symmetry. If you rotate that pattern by just 180 degrees, half a circle, it looks exactly the same.
Wait, walk me through that. If you rotate it 180 degrees, doesn't the stretching axis now point where the squeezing axis was?
It does, but the pattern itself is the same. The plus shape becomes a plus shape again. A thing that is invariant under 180-degree rotation is, by mathematical definition, a spin 2 field. That's its signature.
So the data from LEGO and other gravitational wave observatories is, in a way, a direct measurement of the spin of the graviton.
It's the best evidence we have. It confirms that gravity is a spin 2 phenomenon.
But just to be absolutely sure, let's run through the process of elimination. Why can't it be anything else? Let's start with spin 0, a scalar particle.
A spin 0 particle would be the simplest possible mediator, but it has a fatal flaw. A scalar field couples to the trace of the stress energy tensor.
The trace being a specific sum of the diagonal elements of that tensor.
Yes. And the problem is, for a pure electromagnetic field for light, the stress energy tensor is traceless. The trace is 0.
Which means a spin 0 gravity would not interact with light.
At all. Photons would fly right past the sun without bending, which, again, we know is false. Eddington's 1919 experiment kills that idea dead. It also gets the orbit of Mercury completely wrong. So spin 0 is out.
Okay. What about spin 1? Electromagnetism is spin 1, mediated by the photon. It works beautifully there. Why not for gravity?
Because spin 1 vector theories have a fundamental rule. Like charges repel and opposite charges attract.
Like 2 electrons pushing each other away.
Right. For gravity, the charge is mass energy. And all mass energy is, as far as we can tell, positive. It's all the same charge.
So if gravity were spin 1, 2 masses should repel each other. The Earth and the Sun should be flying apart.
They should be flying apart. The fact that gravity is universally attracted between any 2 pieces of matter is a complete deal breaker for a spin 1 theory. It's the exact opposite of what a vector boson would do.
So spin 1 is out. What about higher spins? Could it be spin 3 or spin 4?
That's where a very powerful theorem in quantum field theory comes in, called the Weinberg-Witten theorem. It basically puts a hard cap on the spin of massless particles in any consistent interacting theory.
What does it forbid, specifically?
It forbids any consistent theory of a massless particle with spin greater than 2 that has a well-defined, conserved stress-energy tensor.
And gravity definitely needs one of those, because gravitational waves carry energy away from things like merging black holes. We've seen that happen.
They carry energy, so they must have a stress-energy tensor. And the theorem says if you try to build a theory for a massless spin-3 particle that carries energy, the math just breaks down. You can't make it consistent with the principles of relativity.
So spin is capped at 2. We've eliminated 0, 1, and anything greater than 2. We're left with spin 2.
We are. And here's the most mind-blowing part of all. It turns out you don't even have to start with general relativity. If you just start with the basic principles of quantum mechanics and relativity and say, I want to build a consistent theory of an interacting, massless, spin-2 particle, the only theory you can possibly write down is general relativity.
You're kidding.
It's a famous result from Steven Weinberg in the 1960s. The requirements of making the quantum theory of a spin-2 particle work, the symmetries you need, the way it has to interact, they mathematically force you to rediscover the entire geometric structure of Einstein's theory.
So the graviton isn't just a particle in general relativity. The graviton is general relativity, just viewed through a quantum lens.
They're two sides of the same coin. The particle implies the theory, and the theory implies the particle. It's an incredibly beautiful and self-contained piece of logic.
Wow. Okay, now that we've established the graviton's identity as this massless spin-2 entity, we have to talk about what it actually couples to. Because this is what makes gravity so unique and ultimately so weak. We need to talk about the stress-energy tensor.
This is the crucial leap from Newtonian gravity to Einstein's gravity. In Newton's world, the source of gravity is just mass. That's it.
Simple.
In general relativity, the source is, well, everything. It's any form of energy or momentum. And all of that information is packaged into this mathematical object, the stress-energy tensor.
Which is a rank 2 tensor, a 4x4 matrix, which fits perfectly with the fact that the graviton field is also a rank 2 tensor.
They have to match up for the interaction to work. And because this tensor is symmetric, it has 10 independent components. Each one tells gravity what to couple to.
Let's actually go through them, because this is where the richness of GR really comes from.
Absolutely. The first one, $, is the one everyone knows, even if they don't know the name. It's the energy density. In slow-moving situations, that's basically just the mass density. It's the Newtonian part of gravity.
The part that keeps us on the Earth?
Right. But then you look at the other diagonal components, T Del and T23. These represent pressure.
Pressure is a source of gravity. So if I just squeeze a block of rubber, it gets heavier gravitationally.
It does. Not by a lot in that case, but yes. This is a huge effect inside something like a neutron star. The immense internal pressure holding the star up against its own gravity is itself a significant source of more gravity. It's a feedback loop.
That's a wild idea. What's next?
The off-diagonal terms that mix time and space, the T components, these represent momentum density, or energy flux, the flow of energy.
So it's not just the energy sitting there, but also energy on the move, like heat flowing, or even just the momentum of a spinning planet.
All of it. Any flow of energy or momentum curves space-time. This is why light, which is pure energy in motion, is affected by gravity. It's coupling to this part of the tensor.
And the last set, the purely spatial off-diagonal terms, TI dollars.
That's shear stress. Think of it like viscosity or internal friction in a fluid. Even that contributes to the gravitational field. So gravity couples to mass, pressure, momentum, and stress, all 10 forms.
And this universal coupling is what guarantees the equivalence principle, right? The idea that gravity affects all things equally.
It's baked into the math. In any field theory, the source has to be conserved. For gravity, this means the conservation of the stress-energy tensor. And when you work through what that conservation law implies, it forces all forms of matter and energy to follow the same paths, the geodesics in curved spacetime.
It's the reason a feather and a bowling ball fall at the same rate in a vacuum. Gravity doesn't care what they're made of, only about their total stress energy content.
Exactly. The source is universal, so the effect is universal. It all connects.
It's an incredible theoretical package, but the same universality leads to a huge complication that doesn't exist for other forces, this problem of self-coupling.
This is the feature that makes gravity so different and so difficult. Let's go back to the photon. The photon mediates the electromagnetic force, but it has no electric charge itself.
So photons don't directly interact with other photons, they just pass right through each other.
At the most basic level, yes. But gravity is different. The graviton is a packet of energy and momentum. And as we just established, gravity couples to all energy and momentum.
Ah, including the energy and momentum of the gravitons themselves.
Exactly. Gravitons are their own source. They have to couple to other gravitons. This is what makes general relativity a nonlinear theory. The field generates more of the field.
Okay, walk me through what that means for the quantum theory if you're trying to calculate an interaction.
It becomes a complete mess. In the simple linearized version, the interaction is just the graviton field, looking up to the matter.
That's simple enough.
But that graviton field itself has energy. So you have to add its own stress energy, let's call it teminula, to the source term. But that new source term changes the gravitational field, which in turn changes the energy of the field, which means you have to add another correction term.
It's an infinite feedback loop. Every time you try to define the source, you have to include the energy of the field that the source is creating, which changes the source.
It's an infinite series of self-correction diagrams. And here's the second miracle after the Weinberg result. It turns out that if you have the mathematical courage to sum up that entire infinite series of self-interactions,
What do you get?
You get back the full, nonlinear Einstein field equations. The self-coupling isn't a bug, it's the feature that contains the entire geometric richness of general relativity.
The very thing that makes the quantum theory a nightmare is also the deepest confirmation that the theory is correct.
It's the ultimate proof that the graviton, this self-interacting spin-2 particle, is the right way to think about quantizing gravity.
Okay, so we have this theoretically perfect, logically necessary, beautiful particle, and now we have to turn to the grim reality that ensures we can probably never see it. This is the hierarchy problem.
It's all about the sheer mind-numbing weakness of gravity. We talk about energy scales in physics. The scale where we expect quantum gravity to become important, where space-time gets pixelated, is the Planck scale. That's about 10 giga-electron volts, or GeV.
An absolutely colossal energy, far beyond anything we could ever create in a particle accelerator.
And then you have the scale of the other forces, the electroweak scale, which is where the Higgs boson lives. That's around 100 GeV.
So that's a difference of 17 orders of magnitude, 100 million billion times.
It's a desert. A vast chasm in energy between where gravity is strong and where the other forces are. And this energy gap translates directly into an unbelievable gap in force strength.
We have to use the classic analogy. It's the best way to make this tangible. The magnet and the paperclip.
It really is the perfect illustration. So on one side, you have the gravitational force. The agent doing the pulling is the entire planet Earth. 6 times 10 to the 24 kilograms of rock and iron, all pulling down on a single metal paperclip.
An immense gravitational source.
And on the other side, you have the electromagnetic force. The agent is a cheap little refrigerator magnet, a few grams of metal with its electron spins aligned.
And when you bring that tiny magnet close to the paperclip, it lifts it. The electromagnetic force from a few grams of matter completely overpowers the gravitational pull of an entire planet.
It's not even a fair fight. The force from that tiny magnet is orders of magnitude stronger. This isn't some subtle effect. It's a daily demonstration of how absurdly weak gravity is.
Let's put a number on it. If you compare the forces between two protons, the electric repulsion versus their gravitational attraction.
The ratio is the number that defines this problem. The electric force is about 10 times stronger than the gravitational force.
A 1 with 36 zeros after it. A trillion, trillion, trillion.
It's a number so large it's almost meaningless. But that's the handicap gravity is working with, and that extreme weakness has a direct consequence for any potential particle interaction.
It means the probability of a graviton actually interacting with anything is basically zero.
Exactly. The weakness of the force translates into a vanishingly small interaction cross-section. That's the effective target size a particle presents. For a graviton, every piece of matter is essentially transparent.
It's the ultimate ghost particle. It just sails through planets and stars and galaxies as if they aren't even there.
Which is why detecting one is so much harder than detecting, say, a neutrino, which we already think of as a ghost particle.
I remember for a while there was this really elegant idea to explain the hierarchy problem, the theory of large extra dimensions.
The ADD model, yes. It was a very popular idea around the year 2000. It suggested that maybe gravity isn't actually weak. Maybe it's just as strong as the other forces.
But it appears weak to us. How would that work?
The idea was that all the standard model particles, sparks, electrons, photons, are confined to our familiar three-dimensional brain, like characters drawn on a sheet of paper. But gravity, the graviton, is special. It's free to travel in extra hidden spatial dimensions.
So the gravitational force gets diluted. It spreads out into this larger, higher dimensional space, and we only feel the small fraction of it that stays on our brain.
Exactly. If that were true, the fundamental scale of gravity might not be 1019. It could be much, much lower, maybe even close to the electroweak scale.
And if that were the case, we might have been able to see evidence of it at the Large Hadron Collider.
That was the great hope. We'd be looking for signatures of these extra dimensions, like the production of collisive-colliding gravitons, heavier copies of the graviton, which would show up as missing energy in the detectors.
But we've looked, and we haven't found anything.
Nothing. The LHC has placed very, very tight limits on these models, so for now, we're forced back to the original stark conclusion. The Planck scale is way up there, and gravity really is just 10 times weaker than everything else.
Which brings us to the final nail in the coffin. This isn't just an engineering problem. It's not about building a bigger or more sensitive detector. It's a fundamental barrier imposed by physics itself. We have to talk about the Rothman-Bohm limit.
This is the paper from 2006 where they stopped with the hand waving and just did the brutal calculation. They asked if we could build the most perfect, most powerful graviton source and detector allowed by the laws of physics, what's the best we could possibly hope for?
Let's set the scale again. We need to compare the graviton's interaction probability with the next most elusive thing we can detect, the neutrino.
The neutrino's interaction cross-section is tiny. It's about sigma nu approx 1045 text 222. And to detect those, we need to build detectors the size of office buildings, fill them with thousands of tons of ultra-pure water, and bury them a mile underground to shield from other radiation.
And even then, we only catch a handful of them a day.
Right. Now the graviton, the simplest calculation, gives you its cross-section. It's related to the square of the Planck length, which is the fundamental pixel size of space-time, about 1033 centimeters.
So you square that tiny number.
And you get a cross-section of around $10.6622.
Let me get that straight. That's 10 times smaller than a neutrino's. 1,000 billion times less likely to interact.
That's the scale of the impossibility. A neutron star is more transparent to a graviton than a clean pane of glass is to a beam of light.
So in their thought experiment, how did Rothman and Bohm try to overcome this? First, the source. What's the best possible graviton factory in the universe?
You need matter that is as dense as possible and as hot and dynamic as possible. So they chose a young, hot neutron star. It's the densest stable matter we know of.
More massive than our sun, crushed into a ball the size of a city.
And inside its core, the neutrons and protons are smashing into each other at incredible speeds. Every one of these collisions, this acceleration of mass, radiates gravitational energy in the form of gravitons, a process called gravitational bremsstrahlung.
And what's the output? How many gravitons are we talking about?
Their calculations suggested a luminosity of about 1013 to 10 gravitons per second, streaming out in all directions. A flood of gravitons.
10 trillion a second. Okay, that's a good start. Now for the detector. To catch something with a target size of $10.66222, you need a lot of targets.
You need the biggest, densest detector you can possibly imagine. So they proposed a detector with the mass of Jupiter, about 199 times 10 kilograms made of hydrogen, placed as close as possible to the neutron star.
Jupiter mass. Why that specific limit? Why not something bigger?
Because if you make it any more massive, its own gravity will ignite nuclear fusion in its core. Your detector would turn into a star, and the light and heat and neutrinos from that would create an insurmountable background noise. Jupiter is about the maximum mass an object can have and remain a cold, dark body.
Okay, so we have the ultimate source and the ultimate detector pushed to the very edge of physical law. You run the numbers. What's the detection rate?
After you calculate the flux of gravitons hitting the Jupiter detector, multiply by the number of hydrogen atoms in it, and then multiply by that horrifyingly small cross-section, the result is a maximum event rate of about 1 graviton detection every 10 years.
1 event per decade. That's barely non-zero, but it's not zero. Theoretically, it's possible.
That's the signal rate. But we haven't talked about the noise, and this is where the cosmic sensor steps in.
What's the main source of background noise coming from that neutron star?
Neutrinos. The same violent processes in the core that create gravitons also create a biblical flood of neutrinos.
How does the neutrino flux compare to the graviton flux?
The models show that for every single graviton the neutron star emits, it emits about 1014 neutrinos.
Okay, wait. So you have 1014 times more neutrinos hitting your detector. And we already said a neutrino is 10 times more likely to interact than a graviton.
You see the problem. You multiply those two numbers. The flux ratio, 1014 times the interaction probability ratio, $1021. The total noise to signal ratio is 1039. For every one graviton event you're looking for, you will get 10 neutrino events that look almost identical.
A 1 followed by 35 zeros. It's not just a needle in a haystack. The haystack is the size of the known universe, and the needle is a single atom. It's statistically impossible.
The only way to find the graviton signal would be to somehow shield your Jupiter detector from all those neutrinos.
How much shielding would you need to block the neutrino background by 35 orders of magnitude?
Rothman and Bone calculated it. You would need a shield made of solid lead with a thickness of roughly 20 light years.
20 light years of lead.
And here is the punchline, the final, inescapable paradox. What happens if you assemble a sphere of lead that's 20 light years across?
Its own gravity would be unimaginable.
It would instantly exceed its Schwarzschild radius. It would collapse under its own weight to form a supermassive black hole.
So the very act of building a shield to detect the graviton creates a black hole that swallows your experiment and removes it from the observable universe.
The laws of general relativity that predict the graviton's existence also predict the formation of the black hole that makes its detection impossible. Nature has built a perfect self-referential trap. It's a necessary particle that is, by the very laws that demand it, fundamentally and forever unobservable.
Since direct detection is, well, off the table for good, what about indirect methods? Are there any clever loopholes physicists have tried to exploit?
The most well-known idea is something called the Gertzenstein mechanism. It's about a potential mixing between gravity and electromagnetism.
How does that work?
The idea is that in the presence of a very strong magnetic field, a graviton could theoretically convert into a photon, and a photon could convert into a graviton. This little Guy-Dollard left-right gamma oscillation.
So you could, in theory, shoot a beam of gravitons into a giant magnet and see a faint glow of light coming out the other side.
That's the hope. And this mechanism is actually irrelevant for some searches for high-frequency gravitational waves. But for detecting single, random thermal gravitons, like the ones from our neutron star, the conversion probability is just far, far too low.
How low are we talking?
For any magnetic field we could build in a lab, even the most powerful superconducting magnets, the probability of a single graviton converting is something like 1042.
So it doesn't really help us overcome the initial 1066 spot problem. You're still deep in the realm of impossibility.
You'd need a magnetic field as strong as a magnetar stretching across the entire solar system to get a decent conversion rate. It just trades one impossible machine for another.
What about the absolute cutting edge? I've seen some recent papers from 2024 even, talking about using quantum systems themselves as detectors.
It's a new frontier. Instead of trying to detect the kick from a single graviton, the idea is to look for the subtle effect a passing graviton might have on a large macroscopic quantum state. The idea is called induced decoherence.
So you're not looking for the particle, but for the wake it leaves behind in the quantum world.
Precisely. You could take something like a Bose-Einstein condensate, a cloud of millions of atoms all acting like a single quantum object, and you put it in a perfect state of coherence. A passing graviton, even with its tiny interaction, might be enough to jostle that delicate state and cause it to lose coherence in a specific, predictable way.
Using the extreme fragility of a quantum state as an amplifier for the graviton's tiny signal.
It's the most promising theoretical avenue we have. But, and there's always a but, the calculations show that for the effect to be measurable, the mass of your quantum object would need to approach the Planck mass.
Which is big lit, about the mass of a dust mite, right?
Yes, but the key is you'd have to have that entire mass behaving as a single, coherent quantum object. We are nowhere near the technology to create or isolate a quantum state that massive. So the philosophical door is ajar, but the technological key is still science fiction.
This all leads us to a really difficult philosophical place. The physicist Freeman Dyson famously brought this up. If a physical thing, like the graviton, is impossible to detect in principle, not because our tech isn't good enough, but because the laws of nature themselves forbid it, then does it really belong in a scientific theory?
It's the core question of operationalism. The idea that science should only concern itself with things that can be measured. If you can't measure it, does it have a right to be called real? Maybe we should just accept that gravity is a classical phenomenon and there is no graviton.
But if we do that, we're right back at the beginning of our conversation with the paradox of a quantum source creating a classical field.
We are. You can't escape it. If you throw out the graviton, you break the logical consistency of physics. You violate the conservation of energy or the uncertainty principle. The whole structure becomes unstable.
So we're stuck. The consensus is that the graviton must exist to keep the rest of physics from falling apart.
It has to exist to preserve unitarity and consistency. It's a necessary mathematical truth, even if it lives in a part of reality that is permanently cordoned off from our direct observation. It's the ghost that holds the machine together.
So, after all of this, what's the takeaway for you, the person listening and trying to grasp the absolute limits of what we can know? Let's just quickly recap this incredible paradox.
On the one hand, the graviton is a theoretically perfect particle. Its masslessness gives gravity infinite range. Its spin-2 nature is the mathematical seed from which all of general relativity grows, guaranteeing the equivalence principle. It's the key to unification.
But on the other hand, its coupling strength is determined by the Planck scale, making its interaction probability 10 times weaker than any other force, with a cross-section of just $10.66 Einstein.
And as the Rothman-Bohn thought experiment proved, any detector you could design to overcome that weakness would have to be so absurdly massive that the laws of general relativity themselves would demand its immediate collapse into a black hole.
Nature has built the perfect censorship mechanism. The hunt for the fundamental pixel of reality leads you straight into the ultimate gravity well. We're left with a particle that governs the entire cosmos in a mandatory, unbreakable silence.
It's the mathematical bedrock of the universe, but we are forbidden from ever turning over the stone to look at it.
Which leaves us, and you, with one final, provocative question to think about. If a particle is mathematically essential, logically necessary to hold our theories together, but physically impossible to measure by any means we can ever conceive, how should science define its existence? Is reality only what we can observe, or is it also what the logic of the universe demands must be true?
The silence of the graviton forces us to confront the very boundary between what is real and what is knowable.
Thank you for taking this deep dive with us. We'll see you next time.